Welcome to Nous, the podcast where we tackle the deepest questions about the mind. I'm your host, Ilan Goodman, and my guest today is not a neuroscientist or a philosopher. He is, in fact, a professor of computer science, the head of the Department of Computer Science, no less, at the University of Oxford. He joins me to explore some of the ideas from his recent book. In the UK, it's called The Road to Conscious Machines, and in the US, it has just been released under the title A Brief History of Artificial Intelligence: What It Is, Where We Are, and Where We Are Going. Professor Michael Wooldridge, welcome to Nous.
Thank you for inviting me. It's a pleasure to be here.
Now, Mike, I really enjoyed the book. You managed to keep it very accessible, which I was appreciative of. I learned a lot, and I have questions. Let's start with maybe a fairly simple one. We'll see. I know you get pretty frustrated by some of the hype and the nonsense in the way that the media often report news about AI. But so let's try and sort of lay some groundwork. What are we talking about when we talk about AI? In particular, is it just fancy software, or is it something altogether more richer and more sophisticated?
So that's a very, very hard question, because people have been arguing about that for 70 years and nobody owns AI. It's not like there is one school of thought that everybody buys into about what AI is and that we all agree about that. For me, I've been working in the area for 30 years, and in that time, AI has redefined itself. It's changed and it's evolved and it's redefined itself a number of times. But when I try to explain what AI is now, the difficulty that I have a lot of the time is that people think they know what AI is because they watch movies and they read books and, they've seen Terminator and Westworld and so on. And that gives people the idea that what AI is about is kind of the Hollywood dream of AI. And the Hollywood dream of AI, roughly speaking, is that, we have machines which have the full range of intellectual abilities, the full range of abilities that human beings have. The truth is that makes for great movies and great books, but actually it's really, really a tiny little part of the AI story. What the AI story is really mostly about is simply about getting machines to do things which currently require brains and nervous systems and potentially bodies, the things that machines can't currently do, things which are out of the scope of our current capabilities with computers, and for which the standard techniques that we have just don't offer any solutions. And usually these are very, very narrow, focused problems, things like recognizing a face in a picture would be a classic example. And it's a fact now that machines can do that better than human beings can. It's a scientific fact. Machines are now better at recognizing faces in pictures than people are. Automated translation is another example. Driverless cars, it may not seem like a very narrow task, but actually, if you think about it, it really is quite a narrow, very specific and very focused task. So the overwhelming majority of work in AI is about getting machines to do these narrow tasks which currently require brains and for which our the current techniques in computing don't offer any solution.
Fabulous, yeah. Okay, so you've already touched on a couple of examples, and I'm hoping later on in the conversation we can get to some examples of the kind of recent successes of AI. So in particular, I'm thinking of DeepMind's AlphaFold. We can talk about driverless cars. And the other one I'm hoping to talk about is GPT-3, the OpenAI language generating AI, which is on the face of it, very, very impressive. But let's, before we get to sort of exploring those specific examples, your book gives us a kind of historical overview of the progress and the different approaches to AI. And as I was reading, I was trying to think about a way of organizing this conversation that gives us a sense of the overarching question we're thinking about as we look at these different approaches. And here's what I came up with. See if it makes sense to you. How do we capture and encode knowledge along with rules for action or rules for decision making in artificial systems that enables them to do useful things? Following your definition, things which would normally require a human mind. Is that a sort of useful question that requires as an answer kind of dipping into the different phases and waves in the history of AI?
Yeah, I think so. If you look, the history of AI is roughly completely divided into two different approaches. And one of those approaches says if you want to build a machine that can do these things, then the way that you do that is you look at how a human being does that, and you take their expertise, you encode their expertise, the skills that they use to solve that problem, and you encode that in some way, you give that to the machine. So that means that we laboriously go to human experts on, for example, let's stick with the example of translation. You want to translate from French to English. So what you do is you go to a human expert in translation, and you find out how they do it. What are the rules that they use? Well, how do they translate from French to English? What is the expertise that they use? You encode that expertise and you give that to the machine. So what we're doing there is we are actually explicitly writing down, and that's literally what it amounts to, writing down and encoding the knowledge that human expert has. So that, roughly speaking, that's the whole of what's called the symbolic approach to AI does that. And another way of describing that is what you're doing is you're trying to explicitly capture processes like reasoning and planning and problem solving, the sort of conscious mental process of reasoning and planning and problem solving that we sometimes seem to use. And there's lots to love about that idea. One of the things that's very beautiful about it is that it makes that expertise explicit. So you want to know why your program translated something in a particular way. You just could go and look at the knowledge that it used. Look, this is the reasoning that it used to do this translation. And the theory underpinning that is very, very beautiful. It's a kind of beguiling dream, and it held sway in AI for a number of decades. Problem is, for lots of frustratingly simple tasks, it just doesn't work. Where it really didn't work at all is on perception. So, in driverless cars, the entire problem of driverless cars is about perception. It's about knowing where you are and what's around you. If you solve that, I think everything else is really going to be quite straightforward. And symbolic AI was very, very limited when it came to, for example, recognizing faces in pictures or interpreting scenes in a photograph. Or speech understanding, and so any of those tasks that are involving perception, it just was really, really quite bad at. And the incredibly frustrating thing is that we take those for granted. They're not things that require intelligence, as far as we can see. That's one of the great ironies of the name artificial intelligence. The things that proved so hard are the things that don't seem to require intelligence in people at all. The most basic things that we all do. Whereas the success stories of symbolic AI, like mathematical theorem proving programs, they are the kind of the intellectual tasks that scientists tend to value quite highly. We succeeded with those, but we didn't succeed with the most basic ones in symbolic AI. So that's one approach, symbolic AI. What you do is you talk to a human expert, you extract their expertise, and you give that to a machine. And that process of extracting their knowledge and encoding it is called knowledge representation. And a huge amount of work went into what's called knowledge representation. So that's one tradition. The other tradition says, don't model the mind, model the brain. So you look at the microstructure of the brain, and we can see that the brain is made up of billions of highly interconnected cells, neurons that are massively interconnected with each other via synaptic connections and axons. And we know that those massive, very simple information processing units on their own, but when they're massively interconnected, as they are in the brain and the nervous system, they are capable of learning very sophisticated things. So the neural net approach is not about trying to simulate a brain. People have tried to do that, not terribly successfully, but it's just about using those structures, software analogs of those nerve structures, which are very simple information processing units that are massively interconnected in large networks with multiple layers that are feeding into one another. And what you do with those neural networks is you train them. Instead of saying, look, here is the human expertise, what you do is you show them what it is, the task that you're doing. This is an example of a picture of Michael, and this is the name that I want you to come out with when you see a picture that looks like this. And you train it with lots and lots and lots of those examples. And this is the area, neural networks. It's a very old idea again. It goes back to the 1940s originally. It had a resurgence in the 60s and then died out. It had a resurgence in the 1980s and then died out, but it's come back massively this century. And really all the advances in AI that we celebrate at the present moment are all to do with successes in neural networks. These are the systems that have proved so effective at, for example, recognizing faces or doing automated translation. This is where we've made the breakthroughs in perception that proved so difficult for symbolic AI.
Fantastic. Well, you've laid out the terrain there wonderfully, and given us some previews of the strengths and limitations of the different approaches already. So symbolic and non-symbolic approaches broadly is the two camps to encoding this knowledge and arming these systems with knowledge that they can somehow use to do useful stuff. Of course, a fascinating corollary of this question is, how do we do it? How is it that we're so good at this stuff? And I know that's not the question that you're striving to answer in your work, but it's a kind of corollary. It's a sort of parallel question to this, is if we're trying to build these artificial systems, maybe we'll learn something about what's going on in our own minds and what enables us to do these remarkable feats. I mean, you did use the phrase when you were talking about building symbolic systems. You get some human experts who are good at something like translating languages, and you try and figure out, well, how are they doing it? What are the rules they're using? But of course, in many cases, we kind of don't know how we do these things, right? We certainly don't. We like to think we're following some sort of rational process. But one of the things I think that the history of AI shows, as we'll explore, is that it's very hard to get anything done, and it's computationally impossible sometimes to do certain things in various very systematic, rational ways. But I might be using language incorrectly here, but I think I'm broadly on the right lines. So those are some of the sort of wonderful ideas that I want to explore.
Yeah, well, I can jump in on the very first one. I mean, how do people do it? The truth is we don't really know, but here's what we do know. Firstly, we know that people do it much, much, much more efficiently than our current techniques with computers. So when we train a neural network, as I say, we have to throw huge amounts of data, and it's very computationally costly. I mean, one of the things that people worry about is literally how much energy is used in how much CO2 is generated when we're training large neural networks like GPT-3 that we're going to talk about later. So we know that humans can learn from very small numbers of examples. They can generalize very easily. They can play a board game like chess and immediately generalize to other board games, that are similar without much difficulty. And all of those things are tremendously difficult for AI right now. We haven't solved those. So I think there's no answers. There's only speculation, so I can speculate. And I mean, I think the way I would speculate is this. We are, I'm a 54-year-old human being. I mean, I've been busy learning every day. Every moment of my experience on this planet has been training my neural networks, with some successes and some not successes, but never mind. But actually, that's disguising the fact that behind me are billions of years of evolution. Mother Nature has been doing a variation of reinforcement learning, which is one of the key techniques, with thousands upon thousands upon thousands of generations of my ancestors right back to the primordial slime. And the result is this thing, this entity, which exists in the physical environment of planet Earth. And through that evolutionary process, I've essentially been optimized to be able to exist in this planet Earth. And part of that, for example, I've been over that billions of years, and my brain has evolved so that I can very quickly learn about things like physics, about naive physics. I can learn about the way that the world works. The problem is we can't really do that with computers. We can't do this process of evolutionary reinforcement learning with computers. We can't put a driverless car on the road and let it evolve over thousands of generations to learn how to drive successfully. We don't have that privilege. So, I am not born with a huge amount of knowledge, but I certainly do have some hardwired knowledge encoded in my genetic makeup. But I'm born with the ability to learn about the world that we're in. That, I think, and that's not a scientific statement, that's speculation, but that's my speculation about why it is that we are so successful. It's because we have been engineered over a unimaginably vast period of time to be able to learn about and to operate successfully in the world that we're in. And trying to do that by training your laptop in the shed at the end of your garden is not going to achieve the same results.
Are there not ways of developing systems that evolve over time? I mean, it's nothing like human evolution, but are there techniques in AI being explored that use something a bit like an evolutionary process?
Absolutely, they are. And actually, I mentioned reinforcement learning. So let me just say a little bit more about reinforcement learning, which is kind of the same thing. So I don't know if you've seen, I certainly mention it in the book, but if you haven't yet had a look at the videos of DeepMind's breakout playing program, the one that I mentioned in the book, it's fascinating. So DeepMind back in 2014, wrote one program to play about 50 Atari video games. I think it was 48 or 49, 8-bit Atari video games, a video game console from the 1980s. And the crucial thing about what they did is that they had one program, essentially one artificial intelligence program, that was given no knowledge. So in symbolic AI, the way that you would have done that would have been, you would have talked to somebody that played these games and said, how do you play them? Got their expertise, given that to the program, and off you go. They didn't do that. This program went in with no knowledge whatsoever. And the only thing that it saw was the screen, the same screen that you or I see. So literally the lists of pixels that make up the screen and the current score. And the controls it had were just exactly the joystick and fire button control that you would have had. So it went in to play these games, and what it did is it did reinforcement learning. And what that means is basically it starts out by playing randomly, but when it gets a score, when it gets a point, that reinforces its behavior. I've done something good. So what I'm going to do is the next time I face a situation that looks like that, it's going to make it more likely that I do that good thing again. And when you do something bad, similarly, it makes it a bit less likely. Now, that's disguising a lot of mathematics and some large neural networks that went into that reinforcement learning process. Deep reinforcement learning, which is doing reinforcement learning with neural networks, is DeepMind's sort of core technology. But it just repeatedly does that, plays itself again. But what you've got to remember, and in the end, it learned to play Breakout basically better than a human being can do. It plays the game of Breakout optimally, right? And a number of other games, it plays it better than the best human could play those games. Some games it did very badly on, and that's another interesting story about why it did badly on those games. But what it's doing there is, if you think about it in evolutionary terms, it's playing these games thousands of times, and thousands of generations are being wiped out along the way because they're being completely unsuccessful in doing this. But the experience that's gained is then passed on into essentially the next generation. The next time it plays in this game, it's a little bit better than it was before. Imagine the game of Space Invaders. What it means is that in that game of Space Invaders, thousands of generations are just being wiped out instantly before it's managing to do anything, before it manages to learn how to play those games. Now, I say it's okay to do that in a simulated environment. If you've got a closed simulated environment like a video game console, or even the richer games like StarCraft, which is the one that's attracted a lot of attention over the last couple of years, which is a lot more complex game, a lot more intellectually challenging game than a game like Breakout or Space Invaders. They are still constrained, closed environments, and it doesn't matter if you die, basically. But in the real world, it does matter if you die. And that's a huge challenge for reinforcement learning. Now, the obvious thing to do is, well, can we do simulators, which are sort of high fidelity simulators that are much more like the physical world? So there's a lot of energy right now going into building high fidelity simulators for driverless cars. For example, Waymo, Google's driverless car company, that's exactly what they're doing. They're doing millions of hours in simulators, but it isn't the real world. And it doesn't give you the same richness of experience that you have over, as I say, our billions of years of evolution.
So it's interesting that you used this reinforcement learning paradigm as suggesting that it was a sort of parallel process to evolution, which makes some sense. But I guess I hadn't thought of it as such because it's a little bit more like the kind of learning we would do in a lifetime rather than the kind of learning that biological organisms do that's somehow inherited through genetic mechanisms, isn't it? So is there anything more like that kind of...
So there are evolutionary approaches. Genetic algorithms historically has been a part of research in AI, which has certainly seen some successes. In genetic algorithms, you're literally doing sexual reproduction. You're taking two algorithms and kind of doing some kind of merging of them to produce an offspring algorithm, and you then see how that does. And you do a lot of simulations and see what you can evolve. There's a lot of work that's going on what's called evolutionary game theory, which is about trying to understand how, in strategic settings, how you can evolve behaviors that can work well in situations where you've got to compete or cooperate with other agents. So there is work there, but I think the closest analog that I would think of would be reinforcement learning.
Take us back to the golden age of AI. So in your book, you suggest it's 1956 to 1974. Huge excitement, lots of work going on, lots of investment, and that was all symbolic AI. Can you just identify some of the key ideas that emerged, and then perhaps we can talk about this wonderfully hubristic Psych project? Is that how you say it, Psych? Which I love. But yeah, what were the key ideas that emerged, and why did they seem so reasonable and sensible at the time?
So go back to 1950. There were computers, but it was a completely open question about whether you could build computer programs that could learn, that could successfully play games, that could solve problems, that could prove mathematical theorems. There was no evidence that you could do that. And there was a great deal of skepticism, just knee-jerk skepticism about whether that was possible. By the end of that decade, computer programs existed, albeit in rather primitive forms, that could do all of those things. There were computer programs that could successfully prove mathematical theorems, mathematical results that are, beyond, certainly beyond high school level, non-trivial mathematical results. Computer programs could do that by the end of the 1950s. Computer programs could learn by the end of the 1950s. Computer programs could solve problems by the end of the 1950s. So in just that one decade, you'd gone from, is it even possible to have a machine that can learn and plan and solve problems, to, look, here are computer programs that can do that. And I think it was that, just look at this progress that we've made. These things really are possible. Machines really can learn. Machines really can solve problems. So the beautiful example of the time was Samuel's checkers player. Arthur Samuel, IBM employee, wrote, actually is interesting because it was also one of the first machine learning programs, but he wrote a program to play the game of checkers. And, it would beat most casual players. It wouldn't beat an expert, or it wouldn't even beat a good amateur player, but, it would beat me. That's for sure. And a lot of how it did that was by learning to play this game on its own. So just in that one decade, we'd seen these kinds of progress. And I think it felt there was no reason to believe that we weren't just going to see that progress continue. We've gone from nothing to there. There was nothing evident that said it was all going to grind to a halt. But it did grind to a halt.
Can we just explore the Psych project before we get to why it all ground to a halt?
Sure.
Tell us about the Psych project. What was the aspiration, and what were the methods?
So, Psych project was initiated by a very brilliant researcher in the US called Doug Leonard. So Doug's idea was, he became convinced that the fundamental problem of AI was a problem of knowledge. That actually all you needed was enough knowledge, and then you would solve the fundamental problem of AI. In other words, the Hollywood dream of AI, Doug thought, machines that have the full range of capabilities that people have, is fundamentally a problem of knowledge. And if we can give a machine that knowledge in a suitable form, then it would be able to do everything that a human being could do. So he got the funding in the early 1980s. The Psych project was funded. And what they set out to do was to explicitly encode the entirety of human knowledge. Yeah, it's, as I say in the book, sometimes, you think, how on earth did they manage to persuade them to give them the funding? But sometimes it's the really bold ideas that win out. So they had, I wouldn't say armies, but they had rooms full of people writing down explicitly in a special language, the psych language that they use for writing down knowledge, which is a kind of language based on logic. Everything that a reasonably educated human being knows about their world. Absolutely everything. All the knowledge that you either explicitly or implicitly know as you go about your life would have to be encoded and written down. So this is kind of mundane facts, like London is the capital city of England. That cats are often pets, but not always. That if you turn on a tap coloured red, it will produce hot water. All of those things. But actually, as well, all the kind of knowledge about the naive physics. If you drop a ball from your hand, it will fall to the floor. Everything, all the kind of the knowledge that we have, which, as I said earlier, the knowledge that we have been genetically programmed to be able to acquire from our environments over billions and billions of years of evolution, they wanted to write down explicitly, and there would be a rule, a simple expression for each single piece of knowledge. So hundreds of millions of different rules were produced in this process. And it was a very bold dream.
Did they settle on some kind of ontology for the knowledge? So had they separated knowledge into classes of things? I was just thinking about, how do you write the rule that if you let go of a ball, it falls to the floor? I mean, how do you define the floor and the properties of a floor and the ball and the force? And what did they do?
No, well, you've hit on a very big problem for them. I mean, nobody ever tried to organize the sum of consensus human reality before, and that was one of the very big sticking points that they had. And a few years in after they started, they realized that they needed to go back to the starting point and start again. And so they had to come up with a huge ontology, to use the term, which is the standard term that's used in the literature, and think about how all of these things are organized. What are the different classes of object that you're going to talk about, and how are those different classes of object related? And talking about real objects and imaginary objects and mental concepts, all of that kind of stuff had to be explicitly organized into their ontology. And that itself became one of the big millstones around the project's neck. Just that, there's no given solution to that. And as they pointed out, it's not the case that you can just open up an encyclopedia and take it from an encyclopedia, because it's exactly the kind of stuff that just isn't in an encyclopedia. So that was one of the really big, and I think it's probably fair to say, unsolved challenges about the project itself.
Okay, so how did they know that it hadn't worked out? What was the sort of criterion by which it was judged to have failed?
So, well, Leonard believed very optimistically, even by the mid-90s, when the project was a decade underway, that they were tantalizingly close. And I have to say, tantalizingly close is a classic AI misconception, because it feels like you've made progress, as I say, like back in the 1950s, and therefore there's just a sort of that one more leap and we'll get there. So he thought that there would be a point where the system would gain enough traction that actually it would be able to start educating itself, that it really would be able to read books, it would be able to read the encyclopedia, and it would be able to also use the knowledge that it had to generate new knowledge, to make inferences on the knowledge that it had, and that it would just start to sort of gain traction on its own. It never really did that. It was never able to. Read human language and to extract knowledge from books. And there were some experiments, and I talk about one experiment in the book to try to explore Psych's capabilities. And I think the conclusion of those were that Psych did have lots of knowledge, but actually there were gaps in its knowledge, and a tiny gap, just one missing rule that connected two completely different areas. And it would be unable to make the most mundane inferences. Like, for example, I think the example in the book, I don't remember exactly, but the example that they used was, is bread food? Just completely mundane things like that Psych struggled with, that a human would have no difficulty with. Because in humans, we don't have those simple little rules. our knowledge is organized in a hugely decentralized way in the vast neural networks in our brains. And our brain isn't just one big neural network. It's a lot of different neural networks that are organized into a range of different ways. And neural networks don't fall prey to that problem. You destroy one neuron in your brain, it doesn't make the whole thing fall apart. You destroy one key rule in psych, and bang, the whole thing falls apart.
Mm. There was another quite sort of small, almost trivial example quite early on in your book that I really enjoyed, because I felt like it illustrated the challenge of a certain form of computation. So it's this idea of sorting numbers into a list in ascending order, right? What would seem to be a trivial task. It's the sort of thing. It's like the simplest possible thing we could imagine a computer doing these days. Like, it's just absolutely basic. But I enjoyed learning that there's one sort of obvious way of doing that turns out to be really computationally demanding. And then it was an algorithm called quicksort was only developed in the 50s, and it's I think the one we still use today, right? So can you explain that difference? That what's the obvious, the most intuitive way, perhaps, if you sat someone down and they were just learning about programming, giving computers simple instructions in a programming language to sort a list of numbers into ascending order? What a basic task. What's the obvious solution to that actually is computationally rather hard work?
So there are lots of different simple ways of doing it, but the one that most people seem to pick on is something called bubble sort, which is, the idea is you start with, so you've got your list of numbers and you start with the bottom two, and these are not in any order. And the task is to get them in, largest number at the top, smallest number at the bottom, let's say. So what you do is you start with the bottom two numbers, and if they are in the right order, you leave them alone and you go on to the next one. But if they're not in the right order, you flip them around and then you go on to the next one. Now, if you flip them around, then what you've done is you've moved the larger number up one place, and then you've then moved one up in your list, and you just do the same thing again. Are they in the right order? If they're in the right order, leave them alone. If they're not, then flip. And it's called bubble because the large numbers will get passed up the list in that way. So the larger number goes to the top of the list until it gets to the top. The problem is that what you have to do is you have to do the same thing again, because the list isn't going to be in the right order. It's going to be in a better order. What you will have done is you'll have got the largest number to the top. So you then have to go through it again, and you then have to go through it again. But each time you know that you've moved the largest number in the remainder of the list to the top. So the list is getting shorter that you have to process. And for large lists, if you're trying to sort, if your list is, the population of the United Kingdom, that's not going to be a feasible way of doing it. It's just going to take too much time. Quicksort is not an intuitive algorithm. I have to say, I think Quicksort is not an AI algorithm. It's an algorithm. Actually, it was invented, I have to say very proudly, by a chap called Tony Hoare. So Tony Hoare, who's my predecessor as head of computer science at Oxford. And I say the remarkable thing about it is that he came up with it in the 1950s. But actually, since then, nobody's managed to do too much better. It's not a simple algorithm, so it's not one that I'm going to try and explain in a podcast. But I think what's interesting there is that is an example of an algorithm which you could get to by sort of sitting down with a blank piece of paper and thinking about it. But lots of the challenges in AI are exactly not of that kind. So if I gave you a blank piece of paper, I think you would come up with something like quicksort. You would come up with a recipe for sorting numbers. If I say, okay, give me a recipe for identifying pictures faces in a picture, I don't think you'd be able to come up with such a recipe. It's a completely different kind of challenge. And it's that different kind of challenge where AI has proved to be so important.
True. Okay, fair point. I think I enjoyed it just because it seemed like such a trivial thing, but actually you realize that, as you say, the quicksort algorithm is really is actually quite complex, but just for this simple task. And it shows you how difficult it is to achieve anything with sets of rules where the kind of, with fixed sets of rules, I guess, which is sort of the symbolic approach, isn't it?
Yes.
All right, so let's jump now to around the turn of the millennium, around 2000. What was going on then, and what was starting to emerge?
what gradually emerged in the first decade of this century and what's exploded subsequently is really three things. So there were some very old ideas, the ideas of neural networks, in particular, basic models that had been put forward in the 1980s by Jeff Hinton in Canada, Yann LeCun, Yoshua Bengio, the three people that won the Turing Award, the Nobel Prize for Computing last year for their work. They'd been champions of these ideas in the 80s that had sort of gradually fallen out of favor. But they'd stuck with those ideas, and they found those ideas began to gain traction. And they gained traction for really three reasons. Firstly, there were advances in basic computer power. The computer power that you need to train a neural network is now very, very cheap. And just that in itself made things possible with neural networks that hadn't been possible a decade earlier. Secondly, I think there was an appreciation of the importance of data. And having, data is essential for neural networks. Without data, you're nothing in a neural network. I say we're building a neural network means training it. Training a neural network to recognizing a face means showing a picture of that face and the name that you want the neural network to produce when it looks at that face. But you need lots and lots and lots of those examples. So what's happened this century? Well, every time we upload a picture of ourselves to social media and we helpfully label it with our name, we are literally feeding their machine learning algorithms. We're feeding their neural networks. We're giving them training data. We're now in the age of big data. So large data sets, very, very large data sets suitable for training neural networks became very widely available. And I talk about these. One of the most famous of these is a data set called ImageNet, which is a publicly available data set, which is just images of everyday things like frisbees, kettles, tables, chairs, thousands and thousands of these images which have been labeled and which you can use for training neural networks. And it was the provision of that data set that was a huge advance in the neural net community. And then finally, there's the deep learning, which is the AI technology of the day. There were some scientific advances, some basic scientific advances in training neural networks and new neural network architectures, new ways of organizing neural networks. All of these things came together. So there was the scientific advances, big data, and raw computer power. Those three things just converged and the field started to explode. And it was obvious by sort of 2005 to 2006 that things were beginning to move forward. And by 2012, we began to see the first of the sort of the breakthroughs this century.
Let's talk about a very recent success, which is DeepMind's AlphaFold. I don't know if it's officially called AlphaFold 2, but they entered that competition twice, and it was the recent one that was deemed to have kind of solved the problem of the three-dimensional shape of proteins. So from what I understand, they feed it a sequence, a list of amino acids that make up the protein, and the AI can tell you, or it predicts the three-dimensional structure, and these three-dimensional structures are immensely complex. They're very, very long, and they're winding all over the place like a sort of crazy bit of string. And the structure is absolutely essential for understanding the function and designing drugs to target it. So it's a very, very useful thing, and it's been a major problem. What can you tell us about how that AlphaFold works? So is it a neural net, or is it a couple of neural nets?
So I'm not by any means an expert in AlphaFold, and I haven't yet had time to read their papers and give you a detailed answer.
I don't know if they've published the paper on AlphaFold yet. So there's certain sort of broad scale features that I think are known, but I don't think they've given a detailed breakdown. But yeah, just a sort of general idea.
So, well, my understanding is indeed it is neural networks. I mean, what I don't know is how those are organized, but I can tell you based on I could predict based on sort of previous DeepMind work that they will be a number of different networks that are working together to do different sort of functional tasks within the problem. I mean, what for me, the protein folding is a nice example because it is a classic example of a problem that if you just try and approach using kind of conventional programming approaches, you just won't get anywhere because, as you say, these structures are so complex. The space of possibilities that you have to explore is just utterly infeasible. And so you need something completely new. And I think that's where, you need something completely different, I should say. So that's where the techniques come in. But I'm afraid I can't give you any great insights into, I haven't yet had a chance to sort of look at that in more detail.
So one of the things that's interesting about this is it's still a very, very narrow and specific function, isn't it? And in some ways, I think for a wider audience, it's kind of rather disappointing. I mean, you're doing what machine learning seems to be good at doing. You're going from an input to an output. Once you've trained the model, it's fairly static. It doesn't learn, it doesn't adapt, doesn't change. It just executes not a simple function. It executes a very useful function very well, but that's it. And it's a very narrow, specific thing that it can do. And it took years to develop.
Well, I absolutely agree with you. And I think this is one of the big misconceptions about where AI is. I mean, we see something like ProteinFold, the AlphaFold, and we see AlphaGo and the other amazing systems that have been developed. And we see automated translation tools that can do pretty respectable jobs. They won't translate Proust for you, as I talked about in the book, but they will get you around your holiday in Skopelos, or in my case, they'll explain how to switch the air conditioning on in your room in Beijing. And these are all really impressive things, but actually they are all, each of them, very, very narrow in their way. And here's the thing. You can't take the program that plays Breakout and the program that translates from French to English and the program that does protein folding. You can't just take those and add them together and end up with human level general intelligence. The kind of, that's not the way that human level general intelligence is going to arrive. So, I think for those reasons, we are a long way from, the grand dream, what's sometimes called artificial general intelligence. And I'm afraid I'm an artificial general intelligence skeptic. I think we're a long way from that for exactly that reason that you identify.
Yeah. Okay. Well, there's two questions. I want to go on to GPT-3, but before we do, I want to ask you, how does a system like DeepMind AlphaFold or DeepMind AlphaGo, in what way can we say it represents knowledge? How is the knowledge encoded in those systems?
So, well, there's another defining problem of the time, and the short answer is that there's the way that it's represented as a neural network is these very, very large numbers of interconnected, very simple information processing cells, and the connections are weighted basically, which means that we attach numeric numbers representing weights, which just indicates the significance of a particular connection. The larger the number, the greater the significance. And roughly speaking, what each neuron is doing is it's looking at its inputs, and when it's getting a certain pattern of weights of inputs that are active, it looks at the weights, and when they exceed a certain threshold, it fires. It produces an output which feeds into the next level in the neural networks. And that's a very crude way of describing it. Training a neural network reduces to finding what those weights are, what those numbers are. That's all it's about, is these all of the algorithms, and it's a huge area right now, is about finding the most efficient way to find the right weights. So when you see a picture of Wooldridge on the input, that's producing the right output. And the training process just means continually adjusting those weights to try to match so that this input is matched to the correct output. Okay, the problem is what you end up with is a neural network reduces pretty much to a vast number of these numbers. And we don't really know how to interpret those numbers. They don't mean anything to us. We do know, we can see that different parts of neural networks end up being responsible for different parts. So, for example, in facial recognition, there might be a part of the neural network which represents a chin, for example. We can see that sort of neural network is doing that, but we don't have any way of sort of extracting from it. So, well, tell us how you recognize that face, or what are Wooldridge's distinguishing features? The kind of questions that you could ask a human being, you couldn't ask of a neural network. It's one of the defining problems right now of in 2020 of neural networks. The knowledge that they are opaque. They're black boxes. And what makes that, why that's important is, If you're going to use these programs to decide whether somebody should get a bank loan, for example, or I talk about this in the book, whether somebody's going to go to prison, you really don't want them to be opaque. You want to be able to interrogate them. You want to know why they made a particular decision. And at the moment, we can't do that. We're just faced with this big, long list of numbers.
Yeah, fabulous. Okay, so let's talk about GPT-3 now. So we've talked about how DeepMind, AlphaFold, and all of the other sort of famous successes that they've had. They're all systems that do very narrow, specific things. Okay, now GPT-3 was a system launched this year by OpenAI. In the US, and it stands for Generative Pre-trained Transformer. I think I'm right in saying, and it's a language generator. So you can perhaps explain to us what a transformer is in a minute, but it's a language generator. So the way it works is you give it a prompt and it generates language, and it does so with a sort of astonishing degree of skill. Like it sounds very much like a human most of the time. It can generate quite long form pieces. There's a fabulous story about I think it was a PhD student from Berkeley in the US who managed to get GPT-3 to write a series of blog articles that became very popular for a period of time on one website, and people didn't realize that they were generated by GPT-3. It can also do some other astonishing things. It can generate HTML code. I believe it can play some simple games, and it can do some. It sometimes seems to be able to do some sort of causal reasoning, but it breaks down very rapidly when you start probing. Really what it's doing is sensing regularities in language and using grammatical cues. But the point is that it does seem to be able to move between different domains. It's all linguistic, but there is a sort of hint of domain generality in there. And the philosophy website Daily Nous did a wonderful series of pieces with philosophers looking at GPT-3 and thinking about it. And David Chalmers, who's a very eminent philosopher of mind, did say there are sort of elements of domain generality here. It can do a load of different things in areas that you would think are fairly different, and that's astonishing. So it is a very, very impressive achievement, isn't it? But again, give us a sense of how this works, and then perhaps we can talk about what it's really achieved and what its limitations are.
So I think the first thing to say is that I agree. It's a very impressive system. I mean, looking at the examples that are produced, I mean, what's striking for me is if you look at the sort of the longer pieces that are produced, I mean, the sort of things that extend beyond just a sentence or a couple of sentences, what's really dramatic for me is the coherence that actually it holds it together, not just through a sentence, but actually through, paragraphs and even longer. And I think that's, when I first read the examples that were being produced, and you do have to be a little bit careful with, there's some cherry picking goes on very often in the examples that you see online. Yeah. But nevertheless, I think they're genuinely impressive. So I think it's a wonderful achievement. I'm curious. I mean, it's a wonderful technical achievement to build a system it's on a scale. It's a neural network system which is on a scale I think that we haven't seen before. I forget how many parameters they're talking about, but certainly at least 1 billion parameters, which is a huge, that's back in the 1980s, we were dealing with neural nets with just 100 parameters. That was the state of the art then. You can do an awful lot more with GPT-3. But roughly speaking, and this is oversimplifying a little bit, roughly speaking, the way that GPT-3 is trained is by throwing everything at it. It's looked at every text that they could get their hands on, and they've trained it with those texts. So one way of thinking about it is that what you end up with is something like a very fancy autocomplete. I mean, on your phone, when you're typing a text message and it's suggesting possible successor words, one way to think, I mean, this is the GPT-3 people are going to be very cross with me for describing it this way because it's trivializing something which is actually very sophisticated, but it's kind of like a very, very sophisticated autocomplete. The autocomplete on your phone has been trained by just looking at what you do, the text messages that you send, right? So if you send, I'm going to be late a lot, it will learn and suggest that when you said, I'm going to be, it will suggest late, right? GPT-3 is roughly speaking doing the same thing, except that it's been trained not just on your text messages, but on every kind of online text that's available. So I agree, it's very impressive. I think we will still need to do more I think there is a piece of work, and I'd love for you to send me those links. I haven't seen those links to Chalmers. I would love to hear what Chalmers has to say about it. I think there is a piece of work to understand exactly what it is that GPT-3 has learned. But let me say this again, and let me go back to what human beings are and the way that human beings learn. So let me take the example of an omelette, right? So I imagine, I haven't checked this actually, and I should do because I keep using this as an example, so I should check it. GPT-3 has seen every omelette recipe that's ever been produced, right? It's read every omelette recipe. It's read every story in which an omelette appears. It's read every public blog post and whatever in which an omelette is mentioned, right? There's nothing about omelettes that GPT-3 hasn't seen. So what does GPT-3 know about omelettes? Well, you ask it for an omelette recipe, I'm pretty sure it will produce one. But what does it know about an omelette? It doesn't know anything about an omelette. For GPT-3, omelette is just a symbol. It's a symbol it's seen millions of times, right? It's seen and in various different contexts. So in the context of recipes, it's seen the word egg appear and breaking egg and whisking egg and, all that kind of thing. But does it mean anything, the word omelette? I don't think it means anything to GPT-3. An omelette for us is not just a symbol. It's a symbol that we use, but it's a symbol that means something. What does omelette mean for me? It means every experience I've had with an omelette in the real world. Omelettes are not just symbols. They are things which exist in the world. And I've had, hundreds of experiences with omelettes, and we'll have hundreds more experiences with omelettes. And so when the term omelette for me refers to all of those experiences that I've had, all those subjective experiences in the real world that I've had with omelettes and with eggs and all the failed attempts that I've had to make omelettes and the great omelettes I've had in fancy hotels, all of that stuff is what it means to me. GPT-3 doesn't have access to any of that experience. All it's got is learning these linguistic relationships. Now, I completely accept that you can, that learning those linguistic relationships and so on. We certainly do use those when we learn about the world, but there's a huge other side of our learning about the world, which is not available to GPT-3. And it's not just the 54 years of experience that I've had on planet Earth with omelettes, but also the billions of years of evolution, that my ancestors had in breaking eggs and so on. I mean, I'm trivializing a little bit, but you get the point, right? All of that stuff is not available to GPT-3. So it's a wonderful thing, but it's at the moment, it's a kind of curiosity. What I'm curious about, I am curious what GPT-10 is going to look like. That's going to be very interesting. But for it to have understanding in the same way that we have, it's not going to get there just by reading recipes for omelettes. That's not the same as experiencing an omelette in the world. Yes,
exactly. Okay, so does this take us to the idea from Rodney Brooks, who you refer to in the book a lot, that you don't get real intelligence until you have sort of embodied agents causally interacting?
Yes, absolutely. I think as I'm surprised there isn't more debate about Brooks' ideas in the context of all of these things. I think the way Brooks' arguments were interpreted at the end of the 80s and early 90s was kind of a little bit simplistic. It was like, everything must be done in robotics. And I think that wasn't quite the argument that he was making. But I think, I'm not sure whether he would agree in precisely the form that I'm making it there. But that actually a lot of what it means to understand something, I say, can you understand an omelette if you've never experienced one in the real world? I don't think so, no. It doesn't matter how fancy your text generation is. It doesn't matter how many omelette recipes. That's not a substitute for breaking an egg and whisking an egg and experiencing an omelette in the real world.
Yeah. Very good. Okay, so we're coming to the end now, but I just want to just finish with this broad brushstroke. We started with this overarching question: how do we capture and encode knowledge with rules for action or decision making that enables artificial systems to do useful things? And we've talked about the symbolic approach, the strengths and limitations, and the non-symbolic approaches, the neural nets, the machine learning things. What's your sense, and this can be quite broad brushstroke, about where we make progress next, or what combination of those systems gives us the chance for the most rapid kind of progress in this field?
So I think there is, I'm not sure if it's a consensus, that's probably putting it too strong. I mean, I think there is a fairly strong view that somehow the kind of the sub-symbolic neural network world and the symbolic world have to come together. And I think they will do. And it's self-evident, right? Because we're talking in symbols now. I mean, language is symbolic. It must come together somehow. The question for me is how it does that. And what I strongly suspect is that the techniques that were developed over the decades of the symbolic world won't be the techniques that we end up using. We will find out how to do symbolic reasoning with neural networks. And I think that's what some major thinkers in the field also believe, like Yann LeCun. So symbolic and neural approaches will reconcile. My belief is it's not likely to be the way that the symbolic AI researchers have been doing it. And I should say, by the way, historically, I am a symbolic AI researcher. It doesn't mean those techniques don't have value. I say there are some problems in which it's just much more natural to use a symbolic approach. But for progress towards generality, I think, that I certainly think will require those two worlds to somehow come together.
Well, it's been fascinating having the time to interrogate you about your book, Michael. Thank you so much. Thank you for taking the time, and good luck with the book.
Thank you. It was a pleasure.